he has been one of the world's leader in the research of the unconventional superconductor and multi-component condensate. And after holding appointments in Princeton and Nordita for the last 3 decades and a half, he has been based at Northwestern University. And in recent years, actually starting with the pandemic years, he has been deputy director at Northwestern for the National Quantum Initiative Center for Superconducting Material and Systems. And I presume that he has grown his beard and mustache after assuming this position. Is that right? But anyway.
A little before.
Oh. Yeah, and I mean, considering Jim's research, the last thing I want to add is that I mean, he has been his research has been really applied to a huge range of physics, starting from helium-3 liquid, ultra cold helium-3 liquid, to ultra cold atoms, to all the way down to neutron stars. And today he's going to give us this talk about edge state solitons and novel phases of topological superfluids. And let us all welcome Jim.
Okay, thank you, Sukpo. Should I can share my screen now, right?
Yes.
Okay. All right. Can you see the presentation mode?
Yes.
Okay, well, thank you, Sukpom, and all of the members of this center and the IBS Physics Center. I'm delighted to be able to participate in this workshop, and today I'm going to talk about edge states and novel phases of topological superfluids. And some of those states do include domain wall phases and embedded soliton structures. So as Supam said, I'm Jim Sauls at Northwestern University, and I'm going to talk about work that I worked on and also jointly with Hao Wu, who was a former PhD student of mine, and Alexei Shetsov, who's a former postdoc of mine. So I'm going to focus on superfluid helium-3, which actually has two possible grounds, multiple possible ground states, both of which are topological superfluids. I should say that I have been at Northwestern for a while, but in the context of the previous presentation, I should let you know that I will be moving to Louisiana State University, and I'll become the director of a new Hearn Institute for Theoretical Physics. And I hope in the not too distant future, I'll be able to host workshops similar to this one from Baton Rouge, Louisiana. Okay, so let me start. For those of you who may not be completely familiar with superfluid helium-3, I've shown you the pressure temperature phase diagram here in the millikelvin range. The white region here is a normal Fermi liquid, and this first line here is labeled by TC as a line of second order phase transitions to a BCS superfluid, which is spin triplet and is known to be P wave. And there are two possible equilibrium phases of bulk helium-3 labeled A and B here. We know in great detail what the structure of these BCS condensates are. I've shown you here the B phase here, which occupies the largest region of the phase diagram, is the so-called isotropic Balian-Wertheimer phase. And as I said, it's a spin triplet superfluid. So it has three components of the triplet here of the condensate wave function. And I've organized them here into a 2x2 matrix where you can see the orbital structure of each of the three spin components. And the BW phase is quite unique in the sense that it's time reversal invariant because it has the orbital states entangled with the spin states such that the ground state angular momentum is 0. So the residual symmetry of this phase is isotropic under joint spin and orbital rotations and invariant under time inversion. And this indeed is a topological phase. Many people have done some beautiful work on this phase, including Sukbom. And I'm going to not speak today about this phase. I'm going to concentrate on the other phase, which is the A phase here, which is a chiral phase. And this phase breaks spontaneously time reversal symmetry. It also breaks spin rotation symmetry and orbital rotation symmetry, in combination with the U1 gauge symmetry, down to a pair of U1s, and it has a residual discrete symmetry, which is the combination of mirror reflection symmetry and time reversal. So this phase is a chiral phase, which you can see here, it has only 2 of the 3 spin components present with equal magnitude, but with a phase winding in momentum space here, where phi is an orbital angle about this broken symmetry axis, which I call the chiral axis. So this phase is not the ground state in bulk, but if we confine helium-3 into a slab, so this dimension here, D, is the thickness of a film, we can, at any pressure, even low pressures, we can go from the B phase, and under confinement, we can always reach and stabilize the chiral A phase for any pressure. So the absolute ground state of superfluid helium-3 is believed to be this chiral phase that I showed you earlier for film thicknesses that are below about 10 coherence lengths. And to give you an idea of what that physically is, that's about 10 coherence lengths is about 1/10 of a micron. So these are easily achievable film thicknesses in the laboratory. So as I said, the symmetry breaking in 3 dimensions, it looks like this, where we have a nodal point, which is a topologically protected 0 point in 3 dimensions. So you have 0 energy excitations coming from these nodal points. But under confinement, under strong confinement, we can get dimensional quantization of the Fermi surface into a set of Fermi disks. And each disk here is then fully gapped on the Fermi surface. And this becomes a time reversal broken topological phase with Chern number 1. One of the early predictions, going back to Anderson and Morel in 1961, was that the ground state angular momentum of this system, the A phase here, would be finite. And we now know from a lot of theoretical work where it's convincing that the ground state angular momentum is in fact just the total number of fermions of the system divided by 2 times h bar, namely the number of Cooper pairs times h bar. It's an open question experimentally whether or not this is valid, and it would be a great achievement if we had experiments to actually measure the ground state angular momentum. But there may be other ways to get out the nature of this phase, both its symmetry breaking and its non-trivial topology. So let me first remind you of the non-trivial topology of this phase. So here I've written down the Fermionic Hamiltonian for a 2-dimensional version of the helium-3, so a thin film of helium-3. There are a number of proposed electronic analogs for which this discussion may be relevant. We can write this Hamiltonian in Nambu space in terms of in terms of a vector that maps the three-dimensional Nambu space or Nambu spinners or three-dimensional Nambu space, momentum space onto three-dimensional Nambu space. So this vector M here is a vector in this isospin space, which is Nambu or particle hole space. The square of this quantity is non-negative, and for any chemical potential that's non-vanishing. But the interesting point, which to my knowledge was first pointed out by Grisha Volovic in a very nice paper on the connection between 2D chiral superconductors and QED in 2+1 dimensions, was that this is a topological phase with a Chern number that's plus or minus 1 for positive chemical potential, namely for a BCS condensate with a Fermi surface shown here in 2 dimensions as this green circle. It's a trivial chiral BEC, molecular BEC, trivial in the sense that it has no Chern number. Chern number is 0 if the chemical potential is negative. So we're interested in a case, of course, for mu positive, in which case the bulk boundary correspondence tells us that we have to have 0 energy fermions on this boundary, confined on this boundary, and we would like to find some evidence of this non-trivial topology. So one of the interesting features, of course, is that we can consider an edge such as this. And here I've shown a vacuum superfluid interface shown here. So the direction X is into the fluid, and the direction Y is here along the boundary. And the 0 mode is connected continuously to a spectrum of chiral fermions that disperse through the Fermi level. And one of the beautiful predictions, of course, is that at 0 temperature, when we occupy these negative energy states here, we project a net edge current along the boundary. Keep in mind, though, that the edge states that give rise to this net edge current, they're confined on distances of order the coherence length here, which in helium-3 is about 1,000 angstroms or so, or sorry, about a few hundred angstroms or so. So what I've told you so far is that the phases of helium-3A is a beautiful example of spontaneous symmetry breaking and emergent topology, in that the combination of chirality, which is that discrete Z2 symmetry, and topology leads to edge states and chiral edge currents. So what I'm going to tell you in the rest of this talk is about 2 things. I'm going to give you 2 results, is the effect of lateral confinement and edge state hybridization, and how that can lead to new broken symmetry phases. And the second part is on this broken time reversal and parity or mirror reflection symmetry, and how that leads to anomalous transport in helium-3. And I'll connect that back to the existence of these Weyl fermion edge states. So if we have chiral edge currents on the boundary, and we consider a system like this a toroidal geometry here of helium-3A in this torus, then we have edge currents that are counter-propagating on both boundaries. And if the dimensions, all the radial dimensions, are large compared with the coherence length, we can neglect the edge state overlap. And on each edge, we get a sheet current that's quantized. And we can compute then the ground state angular momentum of this system from the sheet current. And that ground state angular momentum, as I said before, is just the number of Cooper pairs in the system times Planck's constant. And that indeed, this edge state physics provides then the local description of a theorem that was proven by McClure and Takagi all the way back in 1979. And so there's a global symmetry argument that was put forth, and it's accommodated by the edge state physics of helium-3A. So this has been a long-standing challenge, is to try and detect this ground state angular momentum. And one of a beautiful idea would be to generalize something like the Clow and Reppe measurement of the persistent current of, say, helium-4. So this would be a persistent current of this kind of bulk toroidal flow, but to generalize that to actually detect the chiral edge current that generates the ground state angular momentum. So a proposed idea is coming from Hyun-Sung Choi at KAIST, and he's been developing an idea for micromechanical gyroscope that will operate down as perhaps as low as 200 microkelvin to measure the ground state angular momentum of the A phase films. So I'll just mention here, one other cool prediction would be, or measurement would be, to see if you can measure the temperature dependence of the angular momentum, not just the overall magnitude, because we have gapless chiral edge states on the boundary. It would predict that you would have a power law drop off in the angular momentum as a function of temperature, and that would be a signature of the linear dispersion of the chiral edge states. So what I want to tell you next is what happens if we think about that torus and we further confine it in the lateral dimension here, D. And now the wave functions for these edge states start to overlap. And what are the consequences of the hybridization of the edge states under lateral confinement of helium-3A? So here I've drawn a two-dimensional cut here. We have one boundary here. We have helium-3 sitting in this region here. The chiral axis is out of the plane. So if this dimension D was very large, we would have a linear dispersing chiral edge branch here with a negative slope, and on the bottom boundary with a positive slope. So that corresponds to the counter propagating chiral edge states on the two boundaries. Now what happens is we make D smaller. Well, the first thing you can do is compute the spatial variations of the condensate amplitudes for this chiral phase. So I've written down the general form of it here. It's basically px plus ipy, but we have spatial variations of the two amplitudes. The amplitude that corresponds to orbitals normal to the boundary has to vanish at the endpoints, and the other amplitude is roughly nearly uniform through the film. Now, what I've shown here is so the calculations that we set up and that Hal carried out was to actually solve the Bogoliubov Hamiltonian or Bogoliubov equations along a classical trajectory, and I've shown one here that reflects back and forth along the two boundary walls. And it's that reflection of these semi-classical trajectories that leads to the hybridization of the states on the two boundaries in this quasi-classical limit. So I'm going to just show you the way in which you can do this and set it up as a map this whole problem. See if I can go backwards. Yep. I'm going to map this problem of multiply reflected semi-classical trajectories onto a full space problem in which we're propagating along a single classical trajectory that goes through a periodic array of domain walls. So so I've shown here the original film is shown here between 0 and 2D, sorry, 0 and D. And then I have a fictitious domain wall here, which corresponds to my physical boundary. So we can carry out this program and calculate the fermionic spectrum and all of the wave functions by this mapping. So what I'm going to show you next then is what happens to the edge currents. So as you can imagine, the edge currents here, if we look at the current density, it's confined on the scale of the coherence length. And when this dimension D starts to become appreciable compared to the coherence length, we get interference between the edge state currents in the center of the boundary, and then we get cancellation and thus reduction of the edge current. So what I'm going to do is show you the plot of the edge current calculated up to half the thickness of the film. So we go from the center where the current is 0 up to the edge. If D was infinity, we get the quantized value as I showed you earlier. And these are the numerical results that Hal produced. D equal to infinity here. So now I have a subscript X. It's the same D I showed you earlier. This is basically the bulk result here for the edge current. So we're not seeing any wave function hybridization or overlap. And then as we start to confine to say 15 coherence length, we see first of all what looks like a suppression of the onset. Well, it is a suppression of the onset, but we see a reduction at 0 temperature of the maximum edge current. And that continues as we continue to confine. And we also find that the edge current completely vanishes at finite temperature for thicknesses of order 10 coherence length or so, and continues as we continue to suppress, to laterally confine the superfluid. So what's going on here is the hybridization gives suppression of the edge currents, and at sufficiently strong confinement, we even in a temperature range here between TC and this first onset, we suppress one of the orbital components and we get what's called a polar phase. We then get reentrance of the chiral phase, and then we return back to the polar phase in this region here around 10. So we can actually map out this phase diagram in some detail. And this red curve here is a result of linear instability analysis, assuming that you go from a homogeneous chiral phase to a homogeneous polar phase. And so you see right around 10, if you sit at lateral confinement of 10 coherence lengths and go down in temperature, you go from polar, chiral, and back to polar. Now that set off alarm bells for us. We thought, okay, this kind of backbending here and this reentrance behavior suggests that something more complex is going on. And indeed, that is true. In fact, there's a whole new phase that opens up, separating the polar and chiral phase here. The polar phase, by the way, is just one component of one orbital. So in the language of people working in topological and unconventional superconductors, this is often called the nematic phase. So this is the phase diagram you get after detailed study, and these are actually computed phase boundaries here separating the polar phase and the chiral phase. And in between here is a phase which I've called the pair density wave phase. It's a pair density wave if we're looking over here at strong confinement near this blue boundary. And it's actually a periodic domain wall phase over here near this boundary here in black called DC1, near the chiral to PDW phase. And it evolves smoothly from a pair density wave phase to a periodic domain wall phase as we tune confinement. So let me show you what the results look like at this particular value of temperature and confinement. These are slices. Over here, this is a stronger confinement. So this is the periodic pair density wave limit. And you can see nice oscillatory, nearly single periodic waves of the order parameter. And what you see here is the chirality of each of these regions shown here. So I've shown the chirality of each one of these regions. And on the boundaries, you can see where how the edge currents are circulating around each one of these half periods. So you have alternating chirality in this periodic array in homogeneous phase. If you go to larger, less confinement, thicker slabs, then what you get is two chiral phases basically separated by a domain wall. And here you see breather modes or solitons that are bound on the domain wall. So this is the limit where we go to a very large period, and we basically separate two otherwise chiral phases with opposite chirality. So we studied these domain walls in some detail. There was actually earlier work by Tsutsumi-san in JLTP on a single domain wall in 3 dimensions. And under confinement, what he showed is something interesting. The lowest energy domain wall of this form here has chirality like this, but it has an edge current on the domain wall flowing in this direction. So that leads to an apparent violation of current conservation. So we went to study this particular structure in more detail and self-consistently. And so what happens actually is that the structure of this domain wall is more complex. It actually has 3 edge currents, 2 of them counter-propagating to this other edge current, and this resolves the apparent current conservation problem. So we've computed all of this self-consistently, and showed that the current pattern here indeed is satisfies current conservation everywhere locally in the entire region. And here you can see those 3 different edge currents here at the domain wall. So quite a remarkable structure, I think, that comes out of this interplay. And at the root of the energetics is a competition in the domain wall energy that traverses the boundaries, and the cost in energy, which you can think of as a domain wall reflected into the unphysical half space. So the domain wall energy density per unit length is actually less for this transverse domain wall than it is for the boundaries. And that gives rise to the stability of these domain wall phases as you approach DC1. So that's, in a nutshell, the predictions that come out of studying the hybridization of these edge states under lateral confinement. We get a new inhomogeneous phase here that's stabilized, which you can think of as a periodic array of domain walls or a pair density wave under a very strong confinement. One other interesting observation is the residual symmetry of the pair density wave phase or periodic domain wall phase. It breaks time reversal symmetry and it breaks translational symmetry, but the combination of a half lattice period and time reversal is a symmetry, very much like that of an antiferromagnet. So you can think of this as an antiferromagnetic realization of a chiral phase. So how am I doing on time, Sukum? Or whoever my host is?
You're doing just fine. Yeah,
Okay.
I think you have like 10 minutes left.
Okay,
So
I'm
we
gonna
have 5 minutes for questions and questions.
So I want to switch gears and show you about a result on the detection of broken time reversal and mirror symmetry in superfluid helium-3 in thick films using electron bubbles. And so I've titled this the anomalous Hall effect for electrons moving in chiral superfluid helium-3. So imagine your universe is a chiral phase with, say, Cooper pairs that are right-handed, P plus IP. And somebody perversely drills a hole in your two-dimensional superfluid, shown here of radius r. Now, for large r, we know that there's an edge current flowing around that boundary, and we can even calculate the sheet current associated with that boundary, and it's this quantized value. And we also know its handedness, namely the edge current is counter-circulating. And we can calculate the angular momentum of this hole. The angular momentum is just minus n over 2 h bar. It's the number of helium atoms, helium-3 atoms removed from the hole divided by 2 times h bar. So the way to think about it, if we move this hole to some different point in space, then we've transported that angular momentum as well. So an object that we implant into helium-3A is going to inherit angular momentum from the pair condensate in the amount of the number of displaced Cooper pairs times h bar. And nature provides us with a brilliant way to do this. You can take electrons, which will bind themselves to the surface of helium, and if you apply a perpendicular electric field, you can push the electron into the helium. And the electron has a very light mass, and it also repels the charged clouds of the helium atoms, and it forms a self-trapped polaron here. It blows a bubble. And the radius of this bubble is about 1.5 nanometers. It corresponds to an object with the charge of the electron now, but with a mass of about 100 helium-3 masses. And we can push the electron bubble through the liquid with an in-plane electric field. We can measure its mobility. And at low temperatures, below about 50 millikelvin, we're in a limit in which the cross-section is so large that the scattering of thermal excitations in the helium is quasi-elastic off of the electron bubble. We can neglect the recoil of the electron bubble. Now, cool thing is, if we go below TC and we cool into the superfluid A phase, the chiral phase, we have a bunch of thermal excitations here, which are chiral fermions. They're the excitations near the nodal points of the chiral phase, and they will scatter off of this electron bubble as we push it through the helium. And so one of the nice predictions by Volodya Mineyev and collaborators was that the symmetry breaking that takes place in the A phase allows for an anomalous Hall term, namely the current of this, the mean value of the current is proportional to the applied electric field times the usual drag mobility, but there's also a transverse component to it that's proportional to this electric field crossed into the chiral axis. And that chiral axis is pinned by the boundary here to be normal to the vacuum or the gas phase liquid boundary. So the L vector here is a pseudo vector, and it plays the role of the effective magnetic field. So the prediction is that you should see a Hall motion, a Hall angle that's related to the ratio of the Hall mobility to the drag mobility. And indeed, this was the motivation for a beautiful set of experiments that were done at RIKEN in Kimitoshi Kono's laboratory and led by Hiroki Ikegami. And what they did was they implanted electron bubbles into the helium, and they drove them in the direction of my mouse here from left to right, or from VN over here to these two other counter electrodes. And they measured the asymmetry of the current. They looked for asymmetry of the current between these two split electrons. So the signature then of Hall motion would be an asymmetry of the current. And indeed, furthermore, that asymmetry should switch sign if you change the direction of the chiral axis. So What I'm showing you here in the center plot are their measurements of the real and imaginary parts of the asymmetry of the current. This was low frequency AC, so they had both quadratures present. So the top line here, where you go from the gray region here into the pink region, you're going from normal phase directly into the chiral A phase. And what you see here is the blue data onsets, and you suddenly get an asymmetry in the current response that persists to the lowest temperature. And the same is true in both quadratures. If you take a trajectory that goes normal to A phase and then into the B phase, then the asymmetry of the current disappears below the AB phase transition. So this, to me, was just a striking, beautiful example of direct evidence for broken P and T symmetry in the A phase of helium-3. And they went and analyzed their data. And here is, in this right-hand plot, is the tangent of the Hall angle as a function of temperature from about 1 millikelvin down to almost 200 microkelvin. So for two different electron densities. So when I saw this, I wanted to understand it in more detail quantitatively, since we have a very good theory of helium-3. And so this is work that Alexei Shevtsov and I did. The basic equation for the mean value of the field, there's of course a stochastic Langevin term here too, which I'm not discussing at the moment. The equation of motion then is the acceleration of the electron bubble driven by the electric field, and the key quantity we want to be able to calculate are is the mean force due to the quasi-particle collisions. So in the limit of low velocities, you can represent that force with a linear coefficient, which is a matrix, and it's just a generalization of the Stokes parameter, but appropriate to an anisotropic superfluid, which has broken P and T symmetry with a chiral axis along the z-axis. And the key thing about this Z2 symmetry that I mentioned before is it allows this Hall contribution, this off-diagonal contribution to the Stokes tensor. So you can recast the equation of motion in the form of the acceleration being driven by the electric field. There's a drag force, a longitudinal drag force, and then there's an effective Lorentz force acting on the electron bubble. And this effective magnetic field, which I call the Weyl field or so forth, is directly proportional to this Stokes parameter eta anomalous Hall, and is along the chiral axis. And here's the amazing thing: the magnitude of this quantity, both theoretically and experimentally, is on the order of 10 to the 3 to 10 to the 4 Tesla. So it's a big effect, and that's why you can see this rather substantial Hall angle. So, so let me just the theory that we developed is a scattering theory, as you can guess, because we're talking about quasi-particle collisions. I'm not going to go through the details of the formulation of the scattering theory, but I should just say that in addition to being able to calculate non-equilibrium properties and kinetic coefficients, we can also calculate the structure of the electron bubble due to its interaction with the condensate. So, the one key important parameter that we have is obtained from the normal state mobility and the helium-3 density, and that gives us the transport cross section, which ultimately is basically pi r squared and determines the ionic radius of the bubble. So these bubbles are mesoscopic. They're large compared with the Fermi wavelength, but they're small compared with the superfluid coherence length. And we know exactly the ionic radius of these bubbles. KFR is 11.17. And that is our one input parameter from from experiment besides TC. So what I've shown here is the density of states as a function of orbital angular momentum quantum number and as a function of energy in units of the maximum gap. So this quantity 0 here, this is the Fermi level. And all of the states in blue are the states that are cold and filled at 0 temperature. And all the states in red are those that are thermal excitations. And you can see the hybridization of these sharp bound states here. There's actually 11 bound states. And these are the discrete finite size version of the chiral branch that I showed earlier for a planar edge. Now we have a sphere, and the appropriate variable here is the angular momentum projection m. So if we fill up all of these states below at negative, all the negative energy states at 0 temperature, we can actually compute directly the edge current density. And so this is Alexi's calculation of the radial dependence of the edge current density. And this is a full quantum calculation, so it's not a quasi-classical limit. And you see here even these atomic scale oscillations as we fill in new shells. And shown over here on the right is the structure of the electron bubble current density, which is circulating left-handed, as I showed in my cartoon. And if you integrate up this current density, here I've shown it plotted at a radius of about 30, kf little r equal to 30, whereas the sphere here is kfr equal to 11.17. Indeed, the angular momentum is basically 100 h-bar. So in addition to our ions being renormalized in mass, they acquire an angular momentum of 100 h-bar from the condensate based on their size. So the kinetics, a key input to the kinetics is computing the differential cross-section or angular distribution for a quasi-particle coming in here from the left, scattering off of our ions sitting here at the center. And here you see the angular distribution over 2 pi. And the red curve is actually the angular distribution for the ion in the normal state. And the blue curve is at temperature below TC, calculated at an energy just above the gap edge. And what you see are the development of two things. First, a massive reduction in the backscattering as you go into the superfluid phase. So what we get here is resonant forward scattering in the superfluid phase. You get an enhancement here. This is a log scale, by the way. And then you see the development of these resonances. And lo and behold, there you should see 11 resonances, one for each phase shift. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and 11. We get 11 resonances. And these resonances correspond to the resonance that's reflected above the bound state energy. So for every bound state, we have a corresponding resonance. And these are the resonance structures in the differential cross-section. The other obvious thing here is the asymmetry in this angular distribution. So on average, there's a higher probability of a quasi-particle scattering in the positive y direction versus the negative y direction. And as a result, there's going to be a net force acting on the ion in the negative y direction. And that indeed is what accounts. This is the Stokes force. This is the Hall contribution. And this is its onset at TC. It onsets linearly, increases rapidly to about 0.8, and then decreases at low temperature with a behavior that depends upon the exact nature of the gap. In this case, we have a nodal point and the two Weyl points. So this is a classic signature for those who are familiar with Andreev or branch conversion scattering. Onset linear, peak at about 0.8, and then rapid drop off at low temperature. So branch conversion scattering turns out to be the essential mechanism by which we transfer angular momentum from the condensate to the ion and give it a transverse force. So over here is the drag force, and you see the drag force drops off extremely rapidly at low temperature as you open up a gap, and also as you get resonant forward scattering on setting. So all of this put together gives us these results that to me were really stunning. Like I said, the one input parameter besides TC is the ionic radius of our electron bubble. And from that input, we can calculate the phase shifts for the ion, and from there we can calculate the drag mobility. And here you see its agreement over about 2.5 decades in mobility, down to about 250 microkelvin. And here is the tangent of the Hall angle as a function of temperature. And while it's not quite as tight a fit, I think it's pretty, to me, it's still a pretty impressive agreement with the experiment for two different electron densities. Unfortunately, the Recan group was not able to go below about 250 microkelvin to test the really low temperature behavior of the Hall mobility, but maybe in the future. So let me summarize, and the results here is electrons in a chiral phase are dressed by a spectrum of chiral fermions. They're left-handed in a right-handed chiral vacuum, giving rise to a spin of negative 100 h bar. The Recan mobility experiments provided direct observation of anomalous Hall effect, and that origin of that is the broken mirror and time reversal symmetry of the helium-3 phase. The theory is a scattering theory of Bogdanov quasiparticles by a dressed ion, and it leads to a prediction for an anomalous Hall field that is remarkably large, of order 10 to the 3 to 10 to the 4th Tesla at intermediate to high temperatures. And there's another direction for future discussion if anybody's interested. This theory has to fail at low temperatures, and the scattering, once we quench out all of the thermal excitations, then new physics has to appear, and that should happen below roughly about 200 microkelvin. So with that, I would stop, and I hope I haven't taken too much. I haven't gone over time, but I would be very happy to answer any questions if there are any. Thank you.
Yeah, I'm afraid Jim has gone up like a minute over the schedule, but I mean, I think it was a great talk, and I still think we can take a couple of questions. Yeah, Hyung-sun, I think I saw your hands first.
Hey, Jim. Thanks for the nice talk. I have a quick question about the first part of your talk. So people trying to do these topological superconductor using topological insulator and superconductor hybrid system. So if they manage to scale their device in the right length scale, would they see the same effect in those nanowire structures? The
Are you talking about in the wires where you have Majorana's on the ends? Is that what you're?
Yeah. So if they scale that up a little to, or thicker wire, if they use thicker wire, would they find the same periodic domain wall structures in those systems?
I don't think so, because that's the dimension that you want to confine for those, for what I think you're talking about, which is you got a wire, a very thin wire laying down on top of a topological insulator, right? Mm-hmm. And you're supposed to then, so the idea is then you're going to, you're basically going to have by proximity a one-dimensional P wave superconductor along the wire, right?
Right.
And then you'll have Majoranas on the two boundaries. So that distance there is typically very large compared with the decay of the scale of the bound state on the two ends. So you're not going to have bound states in the transverse direction. At least I don't think you should, but at least that's my understanding. So you would want to have a two-dimensional system that you could confine laterally. And that two-dimensional system would then have edge states on all boundaries. Then if you laterally confine, you can see this type of competition.
So what I'm saying is you start with these nanowires, and instead of confining it, you're actually making these wires fatter so that they become from quasi 1D to quasi 2D. That's what I'm asking about.
Yeah, well, it depends upon what the nature of the phase that was set up in the quasi 1D case was already a nematic type phase, just 1p orbital along the direction of the wire. So you would hope then if you made it thick in the other direction that you could stabilize a chiral ground state.
Right.
If that's the case, then you can map it onto the helium-3 system I just discussed.
Okay. Thank you.
Okay, and shall we? Yeah, Dan actually raised his hands right after Hyung-Sun, and I assume that he really has an urgent question given that he's the next speaker.
Yeah, I don't have an urgent question. I can ask Jim at another time, but thanks for that talk, Jim.
Thank you, Daniel. I'll be happy
then
to chat with you offline. Yeah, I'm sorry I went long.
Okay, then I think we can just conclude with Segon's question.
Oh yeah, thanks for the nice talk. So this anomalous Hall field is huge. So can there be any other effects due to this very strong magnetic field other than this anomalous Hall scattering?
Yes, good question. I don't have an immediate answer for that. It's not like it's a real magnetic field. It's actually coming from the thermal excitations that are scattering off of this chiral bubble. So I think what you're asking is there another probe I could stick down and test the existence of that field?
Yeah,
that's what I imagine you're asking me. And I don't have anything like a spin probe of the effective magnetic field in my mind, but it's a good thing for me to think about. So thank you, Sekwon.
Thank you. Yeah.
Okay, then let us all thank Jim again for his wonderful